Welcome to Efiwe, excellence without stress.
Welcome guys to Efiwe, excellence without stress. And in today's study we are going to be considering atomic structure and bonding. Now, before we get into it, it's important to know what an atom is. An atom is the smallest part of an element which possesses the properties of that element. And with that said, we get into Dalton's atomic theory. In 1808, John Dalton proposed the atomic theory, which is made up of 5 postulates, which include, first of all elements are made up of small indivisible particles called atoms. Number 2, atoms can neither be created nor destroyed. Number 3, atoms of the same element are alike in every aspect and differ from atoms of all other elements. When atoms combine with other atoms, they do so in simple ratio. All chemical changes result from the combination or the separation of atoms. According to Dalton's atomic theory, atoms were indestructible solid particles. However, experiments involving electrolysis indicates that certain compounds contain charged particles called ions. The formation of ions could not be explained by Dalton's atomic theory, and as a result of this and other observations, scientists had to modify this view. So you will notice that there are so many postulates in Dalton's theory that deviate from the actual thing that happens in nature. Moving ahead, at the beginning of the 20th century, there was the discovery of fundamental subparticles of the atom. And this particular discovery has actually cancelled Dalton's theory of an atom being indivisible. Those particles include electrons, protons, and neutrons. You will notice that every atom is made up of a central nucleus and a surrounding orbit. In the nucleus, you will notice the presence of protons which are positively charged and neutrons, while surrounding it you have electrons found in the orbit. The proton has a positive charge and a relative mass of 1, using carbon-12 as the standard. The electron has a negative charge of the same magnitude as the positive charge on the proton, but then its mass is negligible. How then was an electron discovered? In 1897, J.J. Thomson showed that when a potential difference of 5,000 volts was applied across a glass tube containing a gas at a very low pressure of about 0 to 0.001 atm, the tube began to glow. When the potential difference was increased to 15,000 volts, a bright green glow appeared on the glass. Now, if you look at this structure, this bright green glow is what we refer to as the cathode ray. What do we have to say about that cathode ray? Or what does J.J. Thomson have to say about the cathode ray? Thomson was able to prove that the glow was due to some kind of rays which traveled in straight lines from the cathode. He called these rays the cathode ray. Further experiments showed that cathode rays were composed of only negatively charged particles, and they are capable of producing mechanical motion. They are identical in nature and in the ratio of charge to mass. That is to say, their charge to mass ratio is actually the same thing, irrespective of the nature of the residual gas in the discharge tube or the metals used in the electrode. So the point is this, that the characteristic of that particle was practically the same, and because of that, it is considered a fundamental particle or a building block. Thomson argued that these particles must be the electrons proposed earlier by other scientists to explain conduction of an electric current in wires. So let's talk about the discovery of protons. Since the atoms as a whole is electrically neutral, there must exist inside the atom enough positively charged component to balance the negative charge of the electrons. Yes, it makes sense. The positive ions or the hydrogen ions are called protons. So have that in mind, that if there are electrons with negative charge, there has to be a positive charge to balance it out. And that positive charge that balances it out is what we refer to as the protons. Thomson's model of an atom has that the protons and the electrons are simply found inside a particular sphere. But this particular postulation doesn't account for the presence of an extra atomic particle known as the neutron, which we'll see ahead. So let's consider Rutherford's model of an atom. The model described the atom as a tiny, dense, positively charged core called a nucleus, in which nearly all the mass is concentrated around which light negative constituent called electrons circulate at some distance, much like planets revolving around the sun. So in Rutherford's theory or principle, it's more like you have one core, the central core, and then electrons are revolving around, just as the sun at the center and planets around it. But then this particular theory doesn't account for quantization, which we'll see ahead. Now, in 1885, Röntgen discovered that when high energy electrons in a discharged tube collide with the anode, a penetrating radiation, which he called X-ray, is produced. In 1914, Moseley now found out that he could assign a number called the atomic number to an element based on the frequency of the X-ray the element emits when it is used as the anode of an X-ray tube. Now, he was able to assign the atomic number, and this atomic number is written in the symbol as a subscript towards the left. Superscript towards the left, you have the atomic mass, and the atomic mass is a combination of the number of protons plus the number of neutrons. So take note of that. If, for instance, I tell you that there are 12 protons and 12 neutrons, what is the atomic mass? The atomic mass becomes 12 plus 12, which is equals 24. If I tell you that you have 23 as its atomic mass and 11 protons, how many neutrons will be there? It's quite simple. You have 23. Let's solve that. So as we said, when you are considering the atomic mass is equals the proton plus neutron, which means if the atomic mass is 23 and the proton is 11, your neutron can be found. How? Neutron will be equals 23 minus 11, and you find out that your neutron is equals 12. So that's that basically. So going back to our study. With that said, calculations based on the work of Giger and Marsden indicated that the number of positive charges in the nucleus of an atom was approximately half of this atomic mass. So it accounts for an extra particle inside. Yes, because the protons was just half of the mass, which means there's another particle inside that should balance out and make it complete. Rutherford therefore suggested that particles of zero charges of mass, exactly the same thing as the protons, were present in the nucleus. Now, however, in 1932, Chadwick was able to prove that these particles actually exist by bombarding a thin sheet of beryllium with alpha particles, and there he discovered a new subparticle called the neutron. The neutron had a mass equal to that of the proton, but carried no charge. It also explains the existence of isotopy of an element. Before I move on, when you talk about isotopy is simply a phenomenon in which atoms of the same elements possess the same atomic number or different mass numbers. What do we exactly mean by that? So if you have a situation or a condition where you have chlorine, chlorine has the atomic number 17, and one of them might have 37. Then you have another chlorine atom, 17, but the atomic mass is 35. Notice the same atomic number, but different atomic masses. Different atomic masses. Now, what accounts for the difference in their atomic masses is not the protons, or simply the difference in the number of neutrons. Because if you look for the number of neutrons here, neutrons is equals atomic mass minus proton. So the neutron in the first one is going to be 37 minus 17, and that is 20. While the neutron in the second one is going to be 35 minus 17, and that is 18. So which means that what causes isotopy is difference in the number of neutrons. If, for instance, you are now looking at the relative atomic mass for the neutrons, it will be expressed as, if you are looking for the relative atomic mass for the two atoms, it's going to be given as relative atomic mass is equals percentage 1, or isotopic abundance of the first atomic mass, or first atom, multiplied by its atomic mass 1, added to the percentage 2, multiplied by atomic mass 2, and then all divided by 100. We will probably come across studies with respect to this later on as we go further. Now, moving ahead. So, as I said, Chadwick was able to discover that, and after his discovery, it now aided in our understanding of the atomic structure more. Now, in Rutherford's model of atomic structure, the electrons moved in orbits around the nucleus and were held in their orbits by electrostatic force of attraction to the positively charged nucleus. The attraction varied inversely as the square of the distance between the nucleus and the electron. after Rutherford made his theory did not account for the quantized levels in an atom, and that's where Niels Bohr came in. So Niels Bohr was able to develop Planck's and Einstein's theory and used that particular theory to describe an atom as possessing electrons found in quantized energy level. Rutherford's model of an atom is basically correct, yes, but each spectral line is caused by an electron. That is to say, in describing Planck's and Einstein's account for the spectrum of hydrogen, he noticed that there were particular lines or line spectrum produced, and those line spectrums were produced anytime an electron moves from one energy level to another energy level. The implication is that the energy levels where electrons are found are quantized. Electrons can only exist in circular orbits of definite quantum energy. An electron emits energy in the form of radiation when it moves from a higher to a lower permitted orbit. So this produces a line in the atomic emission spectrum. So if you consider this particular guy and you have this is the ground state and this is a higher energy level, when an electron wants to move from up down, it pushes out energy. It has to release the energy to come down to a lower energy. It's already at a higher energy, so it needs to take away most of those energy for it to be able to come down here. So pushing out this energy, it will go out in the form of your atomic emission spectrum, and that is what Bohr noticed and was able to postulate that electrons were actually found in quantized energy levels. Moving ahead, how do we now find the energy that is given off? It's quite simple. The change in the energy is basically the energy that is given off. So if an electron is moving from a higher energy level to a lower energy level, you simply write the energy level or the energy possessed at a higher energy level minus the energy possessed at a lower energy level. Once you do these differences, you will get the amount of energy that was actually released for it to drop to a lower energy level. Okay, according to Bohr, the electron was restricted to certain energy levels and was thought to move along certain circular orbits around the nucleus. These energy levels were identified by means of principal quantum number. Now, the energy level is what is described by the principal quantum number, and there are four quantum numbers. You have your principal quantum number, your subsidiary quantum number, you have your magnetic quantum number, and then your spin quantum number. So the principal quantum number is basically integer values that are used to denote energy levels or shells in a particular atom. So you have energy level 1, 2, 3, 4, which are the principal quantum numbers basically. And the maximum number of electrons in a shell is expressed or given by the formula 2n squared, where n is the principal quantum number. So moving ahead, we have the subsidiary or azimuthal quantum number. It is expressed as L and has integral values ranging from 0 to n minus 1. So the implication is that when you are considering your azimuthal quantum number, for every value of n given, if we say that the principal quantum number for a particular substance is equals 1, it means that the subsidiary quantum number would be 0 to n minus 1, which we are going to have that L is going to be 0 to 1 minus 1. And if we have that, L is going to be 0 to 0, which is 0. So when you have 1 as the principal quantum number, the number of subsidiaries you are going to have is just 1, and that one has a value of 0. Now mind you, 0 doesn't mean nothing. 0 here is for S subshell. So the other thing you need to take note of is that the subsidiary quantum number describes the subshells. So every number you have for the subsidiary is indicating a particular subshell. So you have 0 is S, 1, when the L value is 0, it is S. When L is equals 1, you have P. When L is equals 2, you have D. When L is equals 3, you have F. So this is the SPDF subshells. So as I said, if you have that P is equals to, the L will range from 0 to n minus 1. Therefore, L will be equals 0 to 1 minus 1. 2 minus 1. And that's going to be 0 to 1. So the implication is that in energy level 2, the energy level 2 can have 0, which is S, and can also have 1, which is P. So that's what this basically means. In a situation where we have P equals 3, when P is equals 3, you will find out that L will be equals 0 to n minus 1. And in that case, L will be equals 0 to 2. So counting that will be 0, 1, and 2. Which means that when I have 3, I have 3, 0, which is 3s. I have 3p, and then I'll have 3d, because 2 is what denotes the value for d subshell in your subsidiary quantum number. And then finally, if you have p equals 4, you'll notice that L will be equals 0 to 4 minus 1, and that would give us 0, 1, 2, and 3. Therefore, for energy level 4, we'll have 4s, we'll have 4p, we'll have 4d, and we'll have 4f. So that's what the subsidiary is just trying to give us subshells. It's just like when you're building a house. In the whole house, they have levels or floors, and that's what this subsidiary tells us. Now, the next one we're going to talk about is the magnetic quantum number. Magnetic quantum number simply describes the number of degenerate orbitals. If you look at this structure now, you will notice that S has only one small block, P has 3 blocks, D has 5 blocks, and F has 7 blocks. How are we able to denote or determine this thing? Quite simple. Let's consider this, for instance. If you have a situation or a condition where you are looking for the magnetic quantum number, magnetic quantum number is denoted by ML. So in this case, if we are looking for the magnetic quantum number, it is given as minus L to plus L. So what does this mean? If I have S subshell and I want to know the number of blocks inside S subshell, how am I going to find it? I'll find it using the magnetic quantum number. What am I right? Okay, so I take it again. S subshell. So if we're looking for S, remember that the L value for S is 0, which means the ML value would be 0, minus 0 to plus 0. And class, minus 0 to plus 0 is still 0, which means that we only have one subshell for S. Let's go to P. If P is represented by the value L equals 1, the implication is that the magnetic quantum number will be from minus 1 to plus 1, which means it is going to be ML equals minus 1, 0, and plus 1. What does this mean? It means that when you are putting up a P subshell will have smaller blocks, 1, 2, and 3. One of them will be minus 1, one of them will be 0, and the other one will be plus 1. Remember, 0 in this case does not mean nothing. 0 is indicating a particular block or degenerate in a substance. So, moving ahead, if we have that we are looking at D subshell, D, L is equals 2 for D, which means that the magnetic quantum number ML will now be equals from minus 2 to plus 2. And that's going to be minus 2, minus 1, 0, plus 1, and plus 2. What is this trying to tell you? That there are going to be 1, 2, 3, 4, 5 blocks for D. So which means in your D block, you are going to have 5 smaller blocks inside. So that's 1, 2, 3, 4. That's 1, 2, 3, 4, 5, basically. Then for your F, in your F, L is equals 3, which means that the magnetic quantum number is going to be from plus 3 to minus 3. And that is going to give us ML equals plus 3, plus 2, plus 1, 0, minus 1, minus 2, and minus 3. Having said this, we have 1, 2, 3, 4, 5, 6, 7 blocks, which means for F, we are going to have 7 degenerate blocks in F. So that's going to 1, 2, 3, 4, 5, 6. So that's that basically. So when you are looking at what the magnetic quantum number does, the magnetic quantum number shows us the number of smaller blocks inside each subshell. Having said that, we go to the next one, which is spin quantum number. Spin quantum number simply describes the direction or orientation of an electron. In each of these small blocks that we represented, each of these small blocks can only contain a maximum of 2 electrons of opposite spin. So the spin quantum number can either be positive half or negative half. That is one facing up while one facing down. So that's that basically about the quantum numbers. Having said that, we are going to be looking at the shapes of S and P orbital. The electrons found in a given shell do not have the same amount of energy. This is because electrons move about the nucleus in different ways. The S electron moves about to produce the effect of a spherical cloud around the nucleus. Thus, the S orbital is spherically symmetrical. If you are going to consider your P, the P has a dumbbell shape. In some cases they call it figure 8, but the point is that it is simply a dumbbell shape. D has a double dumbbell shape, while F has a diffuse shape, which means it is constantly changing. Welcome guys to Efiwe, Excellence Without Stress. And in this section of the study, we are going to be considering the periodic table. Now, the periodic table is simply defined as the arrangement of elements in a vertical column called groups or horizontal rows called periods in order of increasing proton number. So the emphasis here is that when you are considering your periodic table, it's basically an organization or arrangement of elements in the columns and the rows. Remember that if you are doing this arrangement, it has to be in an order of increasing proton number. And we already know that proton number describes the number of protons. So there are 18 groups numbered 1 to 18 and 7 periods numbered 1 to 7 in the periodic table. Point of correction, there are 18 columns. The ones that are referred to as groups are what we refer to as your main group elements, and we are going to be seeing that here. The main group elements are those found in column 1 and 2 and from column 13 to column 18. These ones are referred to as your main group elements, and each column denotes a group. So this is group 1, this is group 2, this is group 3, this is group 4, this is group 5, this is group 6, 7 and 8. These other ones are not necessarily classified as groups. So have that in mind, that once you are referring to your main group elements are in column 1 and 2 and 13 to 18. Moving ahead, you will notice that the periodic table is actually segmented, as we said, into straight vertical columns and then horizontal rows. There are 7 periods of the periodic table, and in the first period we just have 2 elements. In the second period we have 8 elements. In the third period we also have 8 elements. In the fourth period we have 18, fifth period 18, sixth period 32 elements, and then in the seventh period there is a varying number of elements. What are the trends you will notice about the period when you are moving from left to right? The proton number increases from left to right. Obviously, you will notice that calcium here has the proton number of 20, but zinc on this other hand has the proton number of 30. The elements become non-metallic as you are going from left to right. As you notice, calcium here is a metal, but going down to this side, bromine becomes a non-metal. So it's converting from metals to non-metalloids to non-metals basically. So you have that. Then finally, you have that the oxides become more acidic. Why? Because oxides of metals are alkaline and oxides of non-metals are usually acidic. Not all of them though, but most of them are usually acidic. So you have that this side would have your basic oxide or alkaline oxide, while in this side, because there are non-metals here, they will form oxides of non-metals, which in most cases would serve as acidic oxides. Having said that, we go to the next one. Now, there are popular groups of the periodic table or groups with special names, and those groups with special names include your group 1, which is found in column 1, the alkaline metals, group 2, the alkaline earth metals, group 5, which are the pnictogens, they are found in column 15, group 6, which is found in column 16, is the chalcogens, group 7, which is found in column 17, are the halogens, and finally you have your group 8, group 0, or your column 18 elements known as the noble gases. How then can we classify elements besides our groups and periods? We can classify elements by blocks. Yes, and the 4 blocks of the periodic table include S, P, D, F. The S block elements are the elements found in column 1 and 2. So in this first part basically is made up of the S block elements. Then you have here the center block basically is called the D block elements. Here on the far right we have the P block elements, and then finally down here we have the F block elements. The thing you need to take note about these S block elements is that their electronic configuration basically will end with S. If it is a D block element, its electronic configuration will end with D. If it is a P block element, its electronic configuration will end with P. And finally, for F block elements, their electronic configuration will end with F. So have that in mind. This is S, this is P, This is D and this is F. So if I ask you, sulfur is what block element? You will say that sulfur is a P block element. While hydrogen is an S block element, chromium is a D block element, and then you have your europium, which is going to be an F block element. The other class or way of classifying is on the basis of their valency. And as I mentioned, for your main group elements, the number of electrons in the outermost shell corresponds with the group. That is for your main group elements. And finally, we discuss them with respect to their chemical properties. Let's get into it. Alkali metals are the elements found in your group 1 of the periodic table. These metals are basically very reactive and do not occur freely in nature. As I said, if it is a main group element, the group of the element indicates the number of electrons. Hence, for your group 1 elements, which are the alkali metals, they will have just one electron. When they lose that one electron, they tend to form a cation with a charge of +1. The alkali metals are usually soft than most other metals, and cesium and francium are the most reactive elements in the group. Alkali metals can also explode if they are exposed to water. Examples of such metals include lithium, your sodium, your potassium, rubidium, cesium, and francium. We go to the next one, alkaline earth metals. They are found in the second group of the periodic table, and the implication is that they will have 2 valence electrons which will be given out to form a cation which has an oxidation number of +2. They are also very reactive and are not found in most cases free in nature. Examples include your beryllium, magnesium, calcium, strontium, barium, and radium. We talk about your halogens, which are found in column 17. They have 7 electrons in their outermost shell, and this basically implies that they can either give off 7 electrons or accept 1. When they accept 1 electron, they have an oxidation number of -1. Halogens exist as room temperature in all 3 states of matter. For instance, solids, the iodine and astatine are solids, bromine is a liquid, and fluorine and chlorine are gases. Halogens, you will notice, have spellings which end with INA. So fluorine, chlorine, bromine, iodine, and astatine. Those are the examples of your halogens. Then we talk about the noble gases. The noble gases basically are found in the column 18 of the periodic table, and they have completely filled outermost shell. That is the emphasis. For most of the noble gases, they have 8 electrons in their outermost shell, but for helium, it is just 2. Why is that? The first ground shell of any atom basically can take a maximum of 2, and the outermost shell of helium is that ground state shell. Because of that, it would only have 2 for helium to become completely filled. That is why it is also classified as a noble gas. They include helium, neon, argon, krypton, xenon, and radon. Krypton should be a K. Moving ahead, we now talk about classification into metalloids, metals, and non-metals. The elements basically that are found in your first and second column are all metals. Every element found in the middle, which is the D block, are referred to as transition metals. But then when you begin to transit into this side, you start having a formation of your metalloids and then finally your non-metals. So you notice that your metalloids basically have semi-metallic properties as well as some non-metallic properties. Your metalloids are basically also used in the production of your semiconductors, and they are very important parts of the computer and calculator making industries. The metalloids include your boron, silicon, germanium, arsenic, antimony, tellurium, and polonium. When you now consider your non-metals basically are found in column 14 to 16 of the periodic table. They are not able to conduct electricity or heat very well, and they exist in 2 or 3 states of matter. At room temperature, they are gases such as oxygen, and then some of them exist as solid at room temperature, such as your carbon. They have varying oxidation states ranging from +4 or -4 to -1. The non-metals elements include hydrogen, carbon, nitrogen, and so much more that you will find in the periodic table. Finally, let us discuss the differences between metals and non-metals. Metals have high electrical conductivity, while non-metals have poor electrical conductivity. Metals have high thermal conductivity, while non-metals are good insulators, which means low thermal conductivity. Metals are gray or exhibit silver luster, but non-metals do not do that. Metals are all almost solids, or all of them are almost all solids. However, your non-metals could exist as solid, liquids, or gases. Metals can be hammered into sheets, which means they are malleable, but in the case of your non-metals, they are brittle, which means they can break or crack like glass, and they cannot be welded. With this said, we have come to the end of this study. Thank you very much. Hi guys, welcome to Efiwe, Excellence Without Stress. And in this particular study, we are going to be talking about periodicity. Why do we need to talk about periodicity? It's quite simple. With periodicity, you can be able to determine different relationships between elements. For instance, you can be able to know that potassium and sodium would react with water to give off hydrogen gas. But then you would have that aluminium cannot do that, simply because the properties of elements are arranged in trends, and that trend is what we talk about in periodicity. So, what then is periodicity? Periodicity simply refers to the trend or recurring variations in elements' properties with increasing atomic number. So once you are looking at the trends occurring in a periodic table, basically that is what describes periodicity. Before we go further with the study, let's just highlight some things about the periodic table. Now, the periodic table is basically made up of your 18 columns and your 7 rows. Each column basically has a group of elements which usually possess similar properties. Now, the main group elements are found in the first and second column, while the 13th to 18th column holds also the main group element. So you have first and second column and 13th to 18th column. This is what we refer to as the main group elements. Now, each of these main group element columns are referred to as groups. So here we have group 1, group 2. Now, group 3 is column 13, group 4 is column 14, group 5 is column 15, group 6 is column 16, group 7 is column 17, and group 8 is column 18. Your transition metals and inner transition metals are not necessarily classified in groups, basically. So just note that this center part is the transition metals, while this part outside here, which is located here too, is your inner transition metals. So have that in mind. Now, the other thing about the periodic table is that it is also separated into blocks. The first 2 columns is the S block. The 13th to 18th column represents the P block. And what this S block means is that the electronic configuration will end with S. For this guy, the last block of each electronic configuration would be P. Then you have this center part, which is the D block element, and then finally your F block element. So as I said, according to the modern periodic law, the properties of an element are periodic functions of the atomic number. So what this means is that when you are considering periodicity or trend, you are considering the atomic number. Why? Because the properties of every element is simply a periodic function. It is dependent on this atomic number. And this atomic number also refers to the number of protons. What this simply states is the periodic law. Now, in the modern periodic table, as I've discussed, you have your 18 columns and 7 periods, basically arranged in an order of increasing atomic number. And this particular statement I just made is Hofbau's rule of increasing energy level. So, with that said, we shall go on with our study. So, talking about periodicity, as I mentioned, it refers to the trend or recurring variation in elements' properties with increasing atomic number. The properties of elements are a periodic function of the atomic number, as I mentioned, and that is what we refer to as the periodic law. If elements are arranged in an increasing order of the atomic number, there are repetition of properties of elements with similar properties after certain regular intervals, and that is known as periodicity. So when you are talking about periodicity are basically repetitions or trends in a particular group of elements. That's that. Now, the periodic repetition of properties is due to reoccurrence of similar valence shell configuration after regular intervals. Examples of some periodic properties of atoms include melting and boiling point, density, atomic radii or ionic radii, ionization potential, electron affinity, electronegativity, and the rest of them. Talking about the opposite of periodicity, it is known as aperiodicity, and that is when a process or when something is not periodic or not occurring at regular intervals. So let's go back to our periodic table. Now, periodicity is simply based on the configuration of the outermost shell. The similar properties is based on the configuration of the outermost shell.
Elements in the same group have the same number of electrons in their outermost shell, which means group 1 elements will have 1 electron, group 2 elements will have 2, group 3 would have 3, group 4 will have 4, 5, 6, 7, and 8 respectively. So you have that these number of electrons in the outermost shell is what makes every element in this group to have similar properties. In the case of group 1, hydrogen is slightly different though, because hydrogen is a non-metal. But for the rest of them, you have that their properties are very, very similar, simply because they have the same number of electrons in the outermost shell. So let's consider some general periodic trends. The first one is atomic size, radius, and volume. It increases down the group, but decreases across the period from left to right. So what then is atomic size? Simply the size of an atom. And the size of an atom is dependent on its radius. A very important point for you to note is that the size of an atom is dependent on its radius. If we are then to understand what an atomic radius is, an atomic radius is the distance between an atomic nucleus and the outermost shell containing the electrons of the atom. Okay, so let's go to our board to be able to understand this. So illustrating what we just defined on the board, you would have that if you have an atom of an element or two atoms of the same elements, and we measure the distance from the center where the nucleus is found to the outermost electron, which is found in the outermost shell. So you have this basically. So this distance from this center nucleus to the outermost electron is the radius. Now some textbooks could actually define this as half the distance between nucleus of closely positioned atoms of the same element. It actually makes sense, because if you split this distance between these two nucleus, you will get the radius. So have that in mind, that when you're talking about the radius, it's simply the distance from the positive charged nucleus to the outermost electron. Now, as you are going down the group, shells are added, and as those shells are added, for instance, you have in the period 1, like helium, for instance, has just one shell. But then if you go down the group, you will notice other shells are added. So, which means that helium, neon, now has extra shells. So if you're looking at shell configuration, neon has 10 electrons, and that's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So basically, as shells are added, the size of the atom and the radius of the atom increases. So the implication is that when we look at our periodic table, neon is supposed to have a higher atomic size than helium, and argon is supposed to have a higher atomic size than both neon and helium, because shells are increasing going down the group, and that is increasing the size, the radius. As the radius is increasing, volume is dependent on the radius. So as the radius is increasing, the volume of the atom is also increasing. So before we leave this, I would just like to briefly talk about the ionic radius of substances. So the ionic radius basically describes the radius of an ion. So let's consider this. If you have a particular ion, first of all, there are two types of ions. Cations are formed by loss of electron, and metals tend to form cations. Metals form cations. But on the other hand, anions are formed by gain of electrons. And then non-metals tend to form these anions. So moving ahead, if for instance I have a particular, let's consider sodium for instance, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Note, in every form of configuration, the number of electrons is what is used to determine that configuration. So moving ahead, since we have 11 electrons in sodium, you will notice that for sodium to attain an octet state, it either accepts 7 electrons or loses 1. So it's easier for sodium to lose 1, so it loses this one. When it loses this one, it would now become 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is sodium neutral atom, and this is sodium ion. So what are you noticing? That the atomic size actually reduces. So the point you should note about this is that the size of an ion, a cation, is less than the size of its neutral atom. You could put that down. The size of a cation is less than the size of its corresponding neutral atom, because as it loses that electron, the outermost electrons become these ones here. Hence, the distance between the nucleus and that outermost electron will now be reduced. So have that the size of cation is actually less than the size of the neutral atom. On the other hand, the size of anion is larger than the size of its corresponding neutral atom. Now, the second trend we are going to be talking about is electron affinity. Electron affinity, ionization energy, electronegativity, and density increases across the periodic table from left to right, but decreases down the group. So the implication is that if I'm considering the periodic table from left to right, I would have an increase in ionization energy, increase in electron affinity, increase in electronegativity, and an increase in the density. Now, talking about these things, electron affinity is the tendency of an atom to accept an electron, and that's that basically. When you talk about the ionization energy, it is simply the energy that is absorbed for the outermost electron of a particular atom to be ionized or to leave the outermost shell completely. There are first ionization energy, second ionization energy, and the third ionization energy. The first ionization energy is the energy that is required to pull out the first electron. So if another electron is going to be removed from the outermost shell, the energy associated with the removal of that second electron is what we refer to as the second ionization energy. And then the third ionization energy is the energy required to remove the third electron. So we have the first, second, and the third. Now, amongst these three, the lowest is the first, while the highest is the third ionization energy. Now, as we mentioned, ionization energy, electronegativity, all of them increases from left to right across the period. Electronegativity, on the other hand, is what we describe as the tendency of the shared pair of electrons to be attracted to one part or one atom in a given covalent molecule. So basically, if one atom attracts the shared pair to itself, it is referred to as more electronegative, while on the other hand, the one that doesn't attract it to itself is less electronegative. So moving ahead, so you find out that because electronegativity increases across the period, it means that chlorine is more electronegative than sulfur, and sulfur is more electronegative than phosphorus, and the rest of them. Okay, we go to the next trend. The next trend is that the boiling and melting point of atoms increases across the period till the middle for metals. So once you are dealing with metals, the boiling and melting point will increase across the period till it gets to the center. So not like center, but till it gets to the point where your metal ends. So from here to here, there is an increase in the boiling point across the period, going like this. And what is the main reason you have an increase in the boiling point for your metals across the period? The simple reason is because there's an increase in metallic bond across the period. So once you are considering a metallic bond, it's simply formed by cloud of electrons of the outermost shell and the positively charged nucleus. So when you are going across the period, the number of electrons in the outermost shell tend to increase, and because of that increase, there is more cloud, and if there is more cloud, the metallic bond will increase. So have that in mind, that for your metals, the boiling and melting point increases across the period till you get to the middle, not like middle, but gets to the point where the metal stops. So from here to here, you have an increase in the boiling and the melting point for your metals. Now, on the other hand, there is a decrease for your non-metals from the middle to the far right. And this is because there's a decrease in van der Waals force across the period. So what is responsible for the boiling and melting point of non-metals is the van der Waals force. And when it is decreasing, automatically it means that the boiling and melting point will be decreasing. So for your non-metals, there's a decrease in boiling and melting point across the period, while for your metals, there's an increase in melting and boiling point across the period. So it's not like all through, it's just from here to the middle, increase, then from the non-metals to the rest of the part of the periodic table in the period, you'll find out that there will be a decrease. So that's that basically. Then we go to the final one. Electropositivity increases down the group and decreases across the period. Before I tend to leave this particular study, it's important that we note how to write electronic configurations of your atoms and your ions. Very simple. When you discuss electronic configuration, the rules that guide the writing of electronic configuration is Aufbau's principle first. So Aufbau's principle of increasing energy. Then you have your Hund's rule of maximum multiplicity. And then finally, your Pauli's exclusion principle. So talking about the Aufbau's rule, it simply states that electrons enter orbitals in an order of increasing energy level. And to describe that energy level, we are going to be considering what we discussed in quantum numbers. So we have that 1s, the energy level 1, which is the principal quantum number, the L value or the number of subshells in energy level 1 is just 1. As we noted, if you have n equals 1, it means that your L will be equals, you have 0 to bracket n minus 1. So the implication is that in the case of your energy level 1, which is n equals 1, L will be 0 to 1 minus 1. Therefore, L is going to be 0 to 0, which is still 0. Now, this 0 does not mean nothing. This 0 is simply an indication of the fact that you only have one subshell. And that subshell, which has the number L for 0, is S subshell. So in energy level 1, you are just going to have the S subshell. We can also do this for energy level 2. So if we check for energy level 2, that's your n equals 2. We will notice that if n is equals 2, therefore L will be equals 0 to bracket n minus 1. And that is going to be 0 to, okay, sorry about that. So that is going to be, L will now be equals 0 to 2 minus 1. And that is 0 to 1. 0 to 1 simply means 0 and 1. 0 is S, 1 is P. So when you come to energy level 2, you have 2S and 2P. On the other hand, if n is equals 3, you have that L is going to be equals 0 to 3 minus 1. So let's do this. L is equals 0 to 3 minus 1 is 2. And that's going to be 0, 1, 2, basically. 0 is S, 1 is P, and 2 is D. You can do that till F, but basically that's that. So you have 3S, 3P, and 3D. Then we have 4S, 4P, 4D, and 4F. Then we have 5S, 5P, 5D, and 5F. You also have 5G, basically, but we're going to be stopping here for now. So you have 6S, 6P, 7S. Now, to find the order of increasing energy level, just go like this, slant, like this, like this. So just draw your slant line, and then we have the order written. Okay, so writing the order, this is where it starts and going down. So we're going to have 1S. After we are filled with 1S, we'll go to 2S. After 2S, we go to 2P, then 3S. So 2P, then 3S. Then after that, we go to your 3P, 4S, 3P, then 4S. Then we go to 3D, 4P, 5S, 3D, 4P, 5S, and the rest of them, basically. So with that said, we have learned how to write the order for increasing energy level. We'll come to writing the electronic configuration once we are done with understanding these rules. Then Hund's rule. Hund's rule of maximum multiplicity simply states that every degenerate orbital is filled up singly before pairing starts. So in your magnetic quantum number tells you the number of shells, and we've discussed this earlier on. And for the magnetic quantum number, the P subshell has some little blocks. It tells us the number of sub-blocks in the subshell, actually. So the blocks in P is 1, 2, and 3. Now, if I'm to fill the electronic configuration or fill these electrons, I cannot fill 1 and 2 at the same time. This is wrong. I will need to fill 1 first, then fill the other one, and fill this before I start pairing. Take, for instance, I'm supposed to fill this with 4 electrons. I'm not going to write 1, 2, 3, 4. Hund's rule states that they have to fill the degenerate singly before pairing. So I'm going to be 1, 2, 3. All filled before I start pairing, 4. So that's that about Hund's rule. And then finally, Pauli's principle states that a particular orbital can only contain a maximum of 2 electrons of opposite spin, which means if I have a small block here, I can only have 1 electron, and then the second one must be of the opposite spin. So this is wrong. But if I write this 1, 2, this is correct. Okay, with all these things understood, let's get to writing electronic configuration. As I said, electronic configuration is simply the arrangement of electrons in the orbital of a particular atom. So if I am dealing with electronic configuration, I'm not just looking at the number of protons. Take note of that. It is based on the number of electrons. So I'm going to be writing the configuration for the following elements. I have sodium. I have sodium ion. I have calcium, which is 20. I have your let's say nitrogen, which is 7, and then nitrogen ion, basically still proton number of 7. So basically, let's get to that. Now, if I'm going to write the electronic configuration of a particular substance, if it is neutral, the number of protons and number of electrons are the same thing, which means electron equals proton when it is neutral. How do I know that it's neutral? Once there is no charge, it is neutral. So if this is the number of protons or the atomic number, it means that the number of electrons is also 11. So let's get to work. According to Hofbauer's principle, after 1s, how many electrons? 11. So I'll start with s can contain a maximum of 2. So I'll have 1s, it will have 2. Then I go to the next one. After 1s, I have 2s. Now, s contains a maximum of 2. So I filled 4. Out of the 11, I've put 4, which means that what I'll have remaining is 7. So let's keep putting. So we go to 2p. Now, in 2p can contain 6. And because I have 7, I'll put 6 here. And then the remaining one will now enter here. So, what did you notice from this? That this is the electronic configuration of neutral sodium. How did I get it? By filling the electrons according to an order of increasing energy level. Now, if I'm to look at how I filled it in the block, it is going to be 1, 2, S is just 1, 1, 2, then P has 3 degenerate orbitals. That's going to be 1, 2, 3. So 1, 2, 3. Hund's principle. 4, 5, 6. That's how you should fill it. And then finally your S1. So that's that basically. So things to take note of. The number of electrons in the outermost shell indicates the group. So in this case, you have that this number of electrons in the outermost shell. The outermost shell here is shell 3. It indicates the group. So this is going to be a group 1 element. Second thing to note is the outermost shell number or the outermost principal contour number indicates the period, and that is 3, which means that this is in period 3. And then the outermost subshell number or subshell symbol indicates the block. So this is an S block element in period 3 whose group is group 1. Now, for your ions, basically, as I said, it's the same thing. But in the case of sodium ion, you need to find the number of electrons in sodium ion. So let's find that. Now, looking for the number of electrons in sodium ion is going to be very simple. This 11 here is the number of protons and not the number of electrons. So how do we find the number of electrons? This charge is basically equals protons plus electrons, which means if I'm looking for my number of electrons, it's going to be charge minus protons, basically. So it's simple math. So the number of electron is going to be charge, which is plus 1, minus the number of protons, which is 11. Because protons are positively charged, I'll have plus 11, and then that is going to be electrons will now be equals 1 minus 11, and that is minus 10. The minus is simply trying to tell you that electrons are negatively charged, but the number of negatively charged particles are 10. So when writing the electronic configuration of sodium ion, it is now going to be 1s2, 2s2, 2p. Because it's 10, the remaining is like I've written 4 out of 10. What is remaining is 6. I just fill it. So notice that. So that is for sodium ion. So this is for sodium ion, and this basically is for neutral sodium atom. So that's that basically. That you don't just write based on the number of protons. You are writing this based on the number of electrons. Finally, I'm going to write the electronic configuration for this anion. And how do I get to do that? So that's going to be, first, we don't have the number. This is not a neutral particle. So if it was this, then I'll say that the number of protons and electrons are the same thing. But because it's not neutral, I have to find it. And that's charge minus proton. And the number of electrons is going to be equals minus 3 minus the proton, which is plus 7. And that is going to give me minus 10. So how many protons, electrons, I meant to say, are found in nitrogen? You find out that there are 10 electrons in nitrogen ion. So let's get to solve this. So the electronic configuration will now be, for nitrogen 3 minus, will now be 1s2, 2s2, and 2p6. Okay, with this said, before we conclude the class, I would like you to notice something. Did you notice that the electronic configuration of nitrogen ion and sodium ion are the same thing? Yes, they are said to be isoelectronic. So when you have that, the electronic configuration of two substances are the same, basically they are said to be isoelectronic. And there's a general principle or trick I use for this. Once you consider a noble gas, 3 elements behind and 3 elements in front are isoelectronic to a noble gas, which means, looking at the periodic table, if we want to consider this, if you come to the periodic table, you have that if I'm considering neons, neon is isoelectronic to fluorine, oxygen, and nitrogen ions. 3 ions of the elements before, or 3, yes, that's that. 3 ions of the elements before and 3 ions of the elements in front are isoelectronic to the noble gas. So you have that neon will be isoelectronic to fluorine ion, oxygen ion, and nitrogen ion. Please, not fluorine atom, oxygen, and nitrogen. I said fluorine ion, oxygen ion, and nitrogen ion. While neon would also be isoelectronic to sodium ion, magnesium ion, and aluminium ion. That's the basic principle. So 3 ions, anions before, and 3 anions, cations in front in the periodic table would actually give you isoelectronic substance to a particular noble gas. With this, we have come to the end of this class. I hope you learned a lot.